Hello everyone, today we are going to create a LED blink program from scratch. So we are not using any CubeMX, we are not using any standard peripheral libraries. We are creating a bare minimum project for STM32 bluepill series. The microcontroller that I am using is STM32 F103C8, which has 64K flash in it, but the same process will be applicable for any other STM32 microcontroller. You can follow along to create a program from scratch. So let's get started. First of all, let's create a new project. I'm using STM32 KEIL Microvision 5, and let's create a new folder, and just name it EX01. I'm naming it EX01. The project name is also EX01. You can name any more meaningful name that you can think of. I'm just creating this for a tutorial, so I'm just entering a microcontroller name STM32 F103C8, and here is my microcontroller. Here is a range of information about this microcontroller. Just click OK. So because this is created a microvision project for microvision 5, which will be automatically saved as the project will be saved as the extension of UV project X, PROJX. So this will come up with manage a runtime environment. If you are using any previous version, this may not pop up, so you have to migrate the project into microvision 5 for this. So this managed runtime environment will be popped up automatically, but if this will not be popped up automatically, you can pop this out later. Here we are using we are searching for device and startup code, so we need a startup file. This will require the CubeMX core. You can press a resolve button here, so it will automatically resolve or load the CubeMX core, but we can manually go to the CubeMX section and select core. So these two things that we had selected, one is CubeMX core and the second is the startup file. The reason for choosing the microvision is that it supports a very good bare metal programming. So you can also go to this manage runtime environment, or you can go to the project, manage, and then manage a runtime environment. So the same dialog will pop up again. Here you will get the information about the system F103 startup file. Let's hit a compile button, and you will face a one error straightforward, which will says that __RTN32.object reference from undefined symbol main. So this says that undefined symbol main, it means that you have not created any main function which you need to create. So let's create a new add item to the source group 1. You can rename this source group that you can say that user, press F2 to rename, and once you hit enter, it will renamed to your required name that you mention. It doesn't matter what name you enter. I name it user so that it will be more meaningful that I am creating a user specific files under this folder. So add a new item, C file, and I am naming it main. You can specify .c, or you can add without the provided extension. The .c extension will automatically be added. So here you need to create a main function. The start is int and a main. So here hit save, Control S, and compile again, or you can press F7 to build this. Here you will get one warning. So the warning that I need to mention here is the last line of file ends without a new line. So Keil always suggests that any file will be ended with the new line. So you hit enter one more time, and this time if you press F7, hit F7 or press the build button, if you will get no errors and zero errors and zero warnings. It means that you had successfully compiled your project. So the next thing that you need to do is to just add the startup file. If you expand the system underscore STM32F103C8 startup file, this will be, here you will see a header file. If you double click, it will contain all the external references for the microcontroller specific registers. So you can include this header file STM32F10X.H. so as it suggests, it will specify the range of F10X series. So that's all you need, and you can compile again. If you are not sure that which header file you need to include, just hit a compile button, expand the system startup file, and you will see the related STM32F. If you are using F4 or 0 or any other series, it will be there. So that was about creating a minimum project. Now we are ready to start our actual code that will do something useful. So what we need to do here is we are going to blink an LED. The onboard LED is connected to PC13 pin. It means the port C and pin 13. The first thing that we need to know is how we can tackle these LEDs. If you switch from project perspective to a book perspective, it provides documentation for this microcontroller, range of help files, books and documents. The thing that we are using or we need here is, first of all, we need a reference manual and a data sheet. So if you double click on it, it will open up like this. Here you need to scroll down until you find something about the clocking and the GPIO. So we are using two things. First of all, the RCC register. So we need to look at here what a microcontroller STM32 series have. It have for every peripheral it have a clock. So if you do not enable any clock, the any related peripheral will not be enabled. So to enable our peripheral, you need to enable the clock for that respective peripheral. So if we are using the GPIO C, we need to look for the how to enable the clock for the GPIO C. So here if you see that we have a register of clock control register, clock configure register, clock interrupt register. We are not concerned with these registers. What registers we are concerned about is the APB2 clock enable register. So here we see we have two clock enable registers. Any other register we do not have any clock enabling or term with them. But here we have a HB peripheral clock enable register, APB2 peripheral clock enable register, and APB1 peripheral clock enable register. So just to make sure, we can check all these three registers manually, or we can go to the data sheet and look into the, let's open up our data sheet here like this. And if you see that it is medium density performance line ARM based 32-bit microcontroller with 64 or 128 KB flash. So in my case, I'm using the C8 microcontroller, and this 8 denotes that it has 64K memory. But if your microcontroller ends with a letter B, it means that your microcontroller have 128 KB of flash. So be specific to choose the respective microcontroller that you are using. It has a USB CAN and 7 timers, 2 ADCs and 9 COM interfaces. But we are not concerned about these two, are we? No, we are just referring to the GPIO in this tutorial. So just if you scroll down to the GPIO, what it says that each of the GPIO pin can be configured by software as output. So if we are using any GPIO as an output, we have option for using it as a push-pull or open drain. These two terms may confuse you here. but it is very straightforward. If you it is so confusing for you, make sure that you are using it push pull manner most of the time. But what the open drain is, if you come from the electronics background, you may already be familiar with the open drain term. It means that you need to you need to add an external pull up with this pin if you are using for the high current related devices. If you are coming from the 8051 background, it is similar like the using for the port 0 for, and you need to add an external pull-up. But forget this if it confuse you. All you need to remember is that you are using output and as a push-pull manner, what we are going to use in our case. So as an input, if you use this GPIO as an input, you can use it with or without pull up or pull down. So you have a kind of 4 options: with pull up, or with pull down, or without pull up and pull down. It is almost 3 options. Okay. So, or as peripheral alternate functions. So these 3 could be used. So this term may also confuse you. What a peripheral alternate function is, it is basically that if this GPIO is sharing some peripheral like UART, ADC or something, you can use an alternate function in this. But the main actual this term denotes that some peripherals could be redirected to some other GPIOs. So if this makes sense to you at this moment, well and good. But if it doesn't make sense to you, don't worry. At this stage, you will get used to it as you may using STM32 series more and more. So most of the GPIO pins are shared with the digital or analog alternate functions. So as I had told you before, all GPIOs are high current capable except for the analog inputs. So you can use all GPIOs for high current usage, but the analog inputs. The IO alternative function configure can be locked if needed following a specific sequence in order, blah 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 blah. You are not concerned with, and the information that we are looking is here, that IOs on APB2 with up to 18 megahertz toggling speed. What does mean? Ooh, we need to look at this. Well, if you move to the APB2 and it says something about APB2, isn't it? Yeah. So I think we need to go, we should go APB2 peripheral clock enable register like this. Whoa, I think we hit something good. Well, what we found here we see that this register is actually a 32-bit register, but only the lower bits from 0 to 15 are available for us to play with. And also we have bits in the higher for timer 9, 10 and 11, but we are not concerned about the timers, are we, for this tutorial? No, we are not. And what we are concerned is we are concerned with the GPIO C. Where are you? Oh, if I zoom in, this is located here. It is a bit 4 for this register, and if we scroll down to look into it, it says that IO port C clock enable bit. If you set this bit as 0, IO port clock will be disabled. If you set logic high to this bit, the clock for the GPIO C will be enabled. Whoa! We had a congratulations moment. So let's go into here. Okay, so we need to use ABBD. Wait a minute. What this register actually names? Oh, I need to look back. Oh, this is so. What is so? Okay, so the name of the register is RCC underscore APB2 ENR. So we can copy this name here and just paste it here and see. Either we can compile it like this, or we need to do something else. Well, it shows some error, use of undeclared identifier. Okay, we will be looking for this a moment later. and it still says that you face an error. It means that you are not using the correct identifier name, or you are missing some kind of headers that you may need and you are not including. So we need to look into it. Hey, but don't worry, don't get confused. As I have told you that it is under the RCC, because register clock configure status, and this structure contains all the related registers about the clock configuration. So here we have all the related registers, and where this RCC comes from, as you may guess that this is just for the, if you had seen in the section of the content, and here we have this term RCC, reset and clock control. So this means that reset and clock control. So under this RCC we have this register. So if we just end up with this, we have something like this. So instead of using RCC underscore, we are just using RCC and dash and greater than sign. This is just the sign to access the structure variables. So now we have this. What we need to do is we need to enable the 4th bit for this register. So here we can do this. Oh, is it really that simple? Oh, yes, it is really that simple. RCC-APB2ENR and R equal to 1. This means that we are just using this 1, and we are rotating this 1 4 times. Ooh. Is it a good syntax? Well, I'm not sure for now, but just bear with it. So we had enabled the clock. The next thing that we need to do is we need to configure the port C and the pin 13 as an GPIO output. So how we can do this? Let's move to the reference manual once again. And let's move to the GPIO sections. And this is general purpose and alternate function section, and we are concerned with the GPIOs, general purpose IOs. And if we click on this, we will end up in section 9.1 in the reference manual. And here we can see the scary looking diagram for the, if you have time, just sketch your mind with this diagram. I'm not going to do this. No, I'm not. Well, here's a bunch of option for the low density, but we are using the medium density devices. And if you are not sure about the low density, medium density, high density devices, or the naming convention for the STM32 series, well, I'm not sure. I had already uploaded the video. Just check the description, or I am making it very soon. So if it is not available right now, I am going to make it very soon. Just say, let me know in the comments if you are want to video about that or not. Just leave a comment, and don't forget to subscribe to stay tuned. And in the GPIO section, each of the general purpose IO port has 32 configuration register. So here we need to know about some registers very well. So the configuration register is the CRL, CRH. So these are the 2 configuration registers. It says the all registers have the 32 bit. Well, if you haven't followed my STM8 series lectures, I had created STM8 series, which is the 8-bit microcontroller from the STM family, ST Microelectronics company. So the STM8 family, this is the structure and architecture is very similar. If you haven't checked the video and you mind looking at that video, just check the link in the description or search in my video sections about the STM8 family. Well, get back to this, and we have two configuration registers, SCRL and CRH. So we need to configure over the configurations, like we need to use as an input or output, and what kind of input and what kind of output, like push pull, open drain, or with pull up and without pull up. All kind of this stuff is going to be under these two registers. So the next thing is the GPIO IDR and ODR registers, and these two registers are nothing more than input direction and output direction. So if you are writing as an output to the pin, you are dealing with ODR register, and if you are reading what kind of value that GPIO have, you are actually reading the IDR registers. So two 32-bit registers and a 32-bit set reset registers. It means that if you are manually want to set reset, you can to any GPIO, you can use this registers. And if you are concerned with a reset, or you want to write a negative or a 0 to the pin, you can also use this register. So basically dealing with as an output, if you are using as an output, you have three registers to deal with: ODR, BSRR, and BRR. You can stick with ODR, so no, it will not hurt if you stick with ODR, but you can use BSRR and BRR. Where you need to use which register, it is a pain to mind. But you stick with ODR for now. Got it? You will use to when and where later on as you move on the programming further. Well, and a 32-bit locking register. If you had read the manual carefully before, you will be aware that GPIO could be locked. So this is not the lock about the programming, this is about the GPIO function locking. So although we are not dealing with this, what we are dealing with is RCL, RCH, IDR, ODR. So that's all what we concerned here. So here are the options: GPIO input floating, input pull up, input pull down. These three kind of inputs, or one kind of input is analog, and the output open drain, output push pull. These two kind of outputs, and two alternate function as a push pull, or alternate function as an open drain. So to this two kind of alternate functions, and two kind of output functions, and one analog, and three kind of input functions. So all these configurations could be configured in CRL or CRH registers respectively. And if we move down, here is a diagram for the GPIO. There is the push-pull. This is actually a push-pull manner. So here is a push-pull manner. NMOS and PMOS, CMOS is connected, and if you are using a push-pull manner, the both are active. But if you are using an open drain, the upper one will be left open, and you will just be stick with the NMOS or MOSFET. Okay, so move down, and here you have the configuration bit. So for any kind of operation you got with these bits. So as we are using general purpose output in push-pull manner, so we need to make CNF 1 bit 0 and CNF 0 bit 0. So we need to make 0 and 0 to these two bits. Where these bits are and at which register, we are looking in very short moment. And the mode that we are going to use is mode 1 bit will be 0 and mode 0 bit will be 1. So we are going to write a 0 1 to these mode bits. It will configure this GPIO as general purpose output in push-pull manner. And PX ODR register, you can use 0 or 1, doesn't matter. So that's all. CNF 1, CNF 0, mode 1, mode 0. These 4 bits need to be configured. Okay, so here is the mode bits. If you are using it 0 1, like I just say that we are going to write 01 here, it means that max output speed will be 10 megahertz. Or you can use 10, it will say that the speed will be 2 megahertz. Basically you can determine the max output speed. What this mean now? Wait a minute, what this mean now? Well, don't get confused. Actually, all GPIO could serve a maximum output speed. It means that you can toggle GPIO max 2 megahertz if you are using this configuration as 10. But if you are using as 01, you can toggle this pin at 10 megahertz speed, and if you are using 11, you can use 50 megahertz speed. So that much kind of scale wave generation you can make. Okay, so if you are dealing with some very high speed device and you are communicating with a high speed device, you may use 50 megahertz option. But if you are using very low, like blinking analogy, just we can stick with this option of using the 2 megahertz. Okay, so good. Now where these bits actually are, well, as I have told you before, that these bits are lying under the CRL and CRH registers, right? So let's move to them. Now what we need to look for in the reference manual is that where the CRL and CRH registers actually are. If we go down in the GPIO sections, and we will see the section 9.2, which is about the GPIO registers. It tells about where the CRL and CRH registers are. These are right at page 171 and 172. Let's move to page 171 and see the CRL registers. And if you see this registers carefully, it will say that the CNF bits and mod bits. So basically 4 bits are for modifying one output bit. Okay, so if you are reserving 4 bits for one pin, so you need at least 64 bits for 16 bits, right? So that's why we have two 32-bit registers, one CRL and one CRH. So if you are using pin from lower nibble, you may use you need to use CRL register. But if you are using the higher byte, the higher byte, like we are using the pin 13 for the port C, so we need to configure into the CRH registers. So it says that the bit CNFY port 0 configuration bit from 8 to 15. So this will change the behavior of the GPIO pins from 8 to 15. So if you are using port X, like A, B, C, D, like we are using port C, and the pin number from 8, PC8 to PC15, you are configuring those pins in CRH register. So if you are configuring the pins from lower byte, like PC0 to PC7, you are configuring those pins in CRL registers. So the respective bits will be like this. So okay, and so it means that these 4 bits are for PC8. If we are dealing with PC GPIO C CRH register, so this is about the 8, and this is 9, and these for 10 and 11, right? But if we are these last four are for 15 and for 14 and 13. So we need to modify bit 20, 21, 22 and 23. So we need to write to pin 20 is we are using here. We need to write 10 here. Okay, so and in configuration registers because we are using the in output mode, we need to make a mode general purpose output push pull, general purpose output push pull. So we need to use 0, and in CNF we need to write so it says if mod bit is greater than 0, it means it is not an input mode, so it is used an output mode. So we need to configure this CNF bits 00 and mod bits 10. That's what we are using. So mod bits, here are the mod bits. We are writing 21 to 1 and 20 to 0, and for the CNF we are using a 00. So we are writing 23rd bit 0, 22 bit 0 and 20th bit 0. So let's move to the Keil. So here if we write GPIO, because we are dealing the GPIO section, and we say again write an arrow section, and we will look for the we need to provide the GPIO what kind of GPIO, A, B or C. So we are dealing with the GPIO C, and the CRH register, as I had told you before. To write a 0 we need to add a tilde sign, and if equal to, it is negation as well. It is basically and we need to and if equal to, just we did the or equal to, and here we need to and equal to write a 0 on it. And here we need to invert the bits, and here I am going to use these kind of brackets, and I am just need to deal with the bits of 23, 22 and 20, 23, 22 and 20, 23, 22 and 20. So we can also create a macro for writing 0 and writing 1 to the bits. The macro could be sharp define. So if you move to this stack overflow section, here you will see a bunch of options and the macros for this. So we can just copy these two like this, and we are having a bit set and bit clear, and here we can use this function of clearing the bit, or we can directly do this here, or we can add an or statement here like this, and later on we can invert all at once, right? 23, 22 and 21. By default, this register will automatically have these bits as 0, but so it means that we can only set GPIO C and CRH and the bit number 20, 23, 22, let's make sure, 23, 22 and 20 or 21, right? Here we should be writing a bit 20, and here we need to or bit 21. So that will be the case for configuring as an output PC13 as push pull output. So in the while loop, the infinite time, what we need to do is we need to what we need to do, we need to toggle the bit. So to toggle a bit, we need to access the ODR register, and all we have to do to toggle a bit of 13, and we can do this with the XOR statement, and here we can apply a visible delay so that we can see this, or we can leave it for just like this, and we can test a compilation before creating any delay. And let's configure the debugger now, and right click and get options. Here we need to set the target and 8 megahertz crystal and as an output if you wish to create a hex file. And in the debug section, we need to select the ST-Link debugger because we are using the ST-Link, and we can make sure that here it use SW, and we can select reset and run. One more thing to select this and change this 2 to 1 to make sure that we are using 64K, not the 128K version of the device. So hit OK here, and just make sure that your settings have been written properly. Yes, we had it. Okay, and that's all for about the debugger. Now we can plug in our microcontroller, and if you properly see the sound of plugging and your drivers are properly inserted, no U-Link device found, and flash download failed, target has been cancelled. It means that your device is not connected properly, so make sure that your device is properly connected before attempting to download this. I think my settings are not properly written. Just let me change these settings very quick. Okay, let's try download. Yes, it is downloading now, and the code is uploaded. Well, this is running in my microcontroller like this, and for creating let's try to debug this. And for debugging in Keil, it is very straightforward thing, and to debug a code, I think I should leave this for another video. You can check my next video to debug this code in the Keil Microvisions, where I will explain the steps about how to debug the code in the Keil Microvision. So let's see this LED. The red one is and the green one, and if you look closely, that it says that this green one LED for power, and this red one is PC13, which is because it is toggling at very high rate. It seems kind of a slow turn on, but we will see in the debug section how to properly check this code and run, and make sure to watch the next video, which is the part 2 of this tutorial series. Thank you so much for this tutorial, and stay tuned, and don't forget to subscribe and like and leave a comment if you have any question. Thank you.